mainly experimental analysis. So I'm going to start with some overview and model definition, the fatigue test that I have done in order to open the crack, and also for the specimen with the fatigue crack were transferred to the another experimental condition in order to open the crack and visualize the crack by digital image coloration and the electronic spatial pattern interferometry, which is ESPI. And at the end of the process, it was possible to say something about the crack closure based on the displacement and the deformation field, and also by the Elber method, which is very famous in terms of the crack closure analysis. And what is the motivation of this work is related to the crack closure is a hot topic these days in the aeronautic, especially in the launchers and the shuttle, and also in the automotive industry, in order to prevent the further fatigue crack growth in their components. So there are two different optical techniques, digital image coloration and the ESPI, and I chose the MTS specimen, which is with the tension of the Na682 aluminum alloy. And there are several specimens with different crack lengths, but here I only present two of them in order to show you what are the conditions in order to watch the crack closure, or we cannot watch it. So this is the geometry of the LPS specimen, which is with the material property from the literature. It is 80 millimeter. It was manufactured based on the ASTM standard with the W width of 80 and the thickness of 3. So the notch was 16 millimeter. It was manufactured by EDM. And first, the specimen was fatigued at the ratio of 0.1 with a maximum load of 10 kilonewtons. And it was a normal fatigue analysis. So the fatigue, the crack was measured by the two traveling microscope, one of them in front side and the other side of the specimen. So we reached at a certain crack length that we decided to have. And two specimens, one of them is identified with a short crack, MT1, and MT2 with the MT1 with the long crack and MT2 with the short crack. So the fatigue test has been done, and the desired crack length was acquired, measured, documented, and then we have the facility in our laboratory, which is the ESPI. I don't know if you know with the optical method. So ESPI is working with the laser, and it is going to project the laser on the specimen surface, and then the projection is going, and when we load the specimen, the projection of the lights and the laser is going to be captured. So in order to make this analysis in practice, we decided to design this medium rate tensile machine, definitely for this project, in order to be fixed in our environment of the ESPI. So right now, this machine can be in function for other analysis, but in this project, we designed it by ourselves, manufactured, and use it here. So this is the LTS specimen. It was painted to be actually sufficiently good both for ESPI and the digital image coloration, because we made both optical methods at the same time. So we have the specimen actually loaded here in this machine with maximum load, and we put the cameras. One of them is related to the ESPI and the other one is digital image coloration. They are watching the specimen surface at the same time while loaded. And this view that you are watching is related to the ESPI, which is the laser projected on the specimen surface. So the 2 megapixel camera was sufficient for ESPI camera. And ESPI is with the resolution of a nanometer, and digital image coloration can be in the best case of micrometer. So that's why this analysis is a multi-scale analysis. ESPI this is some sequence images that I got with the captured image with the phase map and the filter phase map, and this is the final between the deform and the reference set. So you can see the fringe. Here is the crack. When the fringe starts to have some discontinuity, it means that this is the crack length, crack tip. And by this methodology, it was me and my colleagues try to write the MATLAB code in MATLAB code in order to distinguish this discontinuity. So based on the fracture mechanics, when we have any crack or any defect in the structure, so it is expected to watch some discontinuities due to that kind of defect. So we founded our goal on these discontinuities, and through ESPI outcome, it was possible to detect and identify the crack tip and the notch tip and the crack lengths, and then compared to what we have got from the fatigue test. And this is some detail about the digital image coloration, just separated from the ESPI. So a spaceband, the camera and lens, here we have using a 4 megapixel camera, which is with the 60mm lens and extension tube of 12, and this is the field of view and the expected pattern. It should be, as I told you before, I made a study on the expected pattern in order to be good enough for both DIC and ESPI, because ESPI needs also some painting on the specimen, and the digital image coloration is doing the same. And based on the digital image coloration, again, we put our foundation on the discontinuities. So when we have the discontinuities, we distinguish that there is a crack there. So it was possible also to again, with the MATLAB code, to extract the displacement field and then to measure the crack tip and the crack length, because notch is very visible in digital image coloration. This is for the middle tension specimen with a shorter crack. The verification between the ESPI and digital image coloration, displacement in the loading direction and the deformation following the displacement. So you see that in the first, so they are corresponding to different load levels. The first one, second, and this is the maximum load, and this is almost the minimum load. So you see that here we don't have any type of discontinuity. It means that there is no crack is closed. And once we load it with the further values, the crack is starting to show, and this is the verification between both. This is also the same when we have the deformation. So this is the plasticity induced by the fatigue. We cannot ignore it because it's done when we open the crack, and also here in the first load stage there is no crack visible. So because we don't have the deformation visible also. But the scenario is different from the other specimen with the long crack. It shows that even in the minimum crack, in the minimum load, the crack is open. So it means that the plastic effect is too much dominant on the structure, and it does not allow to close the crack, and the crack has been already stabilized. And the results of the deformation put more evidence on that. So here in the minimum load we have the crack, because here is the notch and here is the crack. Although the crack is not completely open at this stage, we have the crack. And the Elber method also helps us to distinguish the crack. Based on the methodology of Elber, it was possible to consider virtual clip gauges on the specimen when subjected to the fatigue, and then we have the crack. And I chose the shorter crack because we concluded that for the longer crack we don't have any crack closure, but for the shorter crack we have. And we made the specimen. This is done only by the digital image coloration, and we loaded the specimen and unloaded with the same sequence in order to see if the displacement on these clip gauges on these 2 4 points are behaving the same in terms of loading and unloading. And you can see they are more and less the same. But it shouldn't be the same actually in the reality, because we have plasticity different in loading and unloading. But it was very close. And as a conclusion, it said that here with the 300 Newton, we have local opening and closure. It means that the crack starts to open and close in loading and unloading. And when we reach 10% of the maximum load, which is 1 kilonewton, the crack is already fully open. And once we load the specimen up to, from 1K to 10K, this is the widely open region. It means that the crack has already opened, stabilized, and it is with the full region visible by the optical techniques. So, based on this analysis, it is possible to conclude that the crack closure can be studied by optical methods. With the ESPI, it was feasible to get the crack length and the crack tip detected by the discontinuities. And the scenario is the same with the digital image coloration, but digital image coloration was a better approach in order to follow the Elber's methodology in order to put the virtual clip gauges on the specimen and then load it and unload it with the same sequence and reach the force displacement, and then some opinion regarding the minimum load, which is the 3%, 300 Newton, which is the crack in the local and local closure and opening, and 10% of the peak load, which is 1K, to have the full crack open. Of course, the fatigue crack that was generated in this study is very dependent to the load ratio, which initially fatigue in order to open the crack. And this is this project is still ongoing in order to load the specimen with different stress ratio in order to observe and in order to assess the plastic behavior induced by the fatigue, because this is the most important part of the fatigue, the crack closure. So thank you very much for your attention. I hope that you respect the time.
Time for one question, please.
Normally you have the most crack closure is what they, at least what they state, is that for long cracks and stress ratio of 0 or 0.1,
Yes.
then they see the most crack closure. But I can't, can you explain that you don't see
Yes.
that here?
I started with this scenario in the laboratory. I suppose that when I have a full longer crack, so the crack closure should be most visible and should most actually better assessed. But it was not like that because of the plastic effect that it was dominated on the crack flanks. Doesn't allow to crack close. And shorter crack, the scenario is different. We have the less plastic effect, but we need to be very careful with the stress ratio, because the stress ratio was 0.1. I have already made another study with 0.05, and it was a better illustration of the crack closure for the shorter crack. Still, we have the same problem of the long crack. So I'm gonna say that maybe if I continue this study, so maybe we can conclude that for a certain length of the crack which is longer than this value, although the crack is long and the crack closure should be more visible. It is not going to be true for all the specimens with different stress ratio and also material, because this is aluminum, and a better study should be done on the morphography of the voids and the microstructure. So this also helps in order to justify the reason.
Do you still think then if you go to stress ratio 0.4 and 0.7 or so, for example, that you can explain those differences in crack rate with crack closure?
It is ongoing now. I'm doing the test.